Hi, I'm Ruth. Thank you very much for coming to my poster about the psychophysiological mechanisms of real-world time experience. Today I'm going to talk to you about a study that we did, which was funded by the British Academy, to try and understand why it is that time distorts during normal daily life. So you will know from your own experience that your sense of time is really fallible. Sometimes events feel like they're passing really quickly, and sometimes they feel like they're dragging by. Theoretical models of timing have suggested that we experience these distortions to time because of changes in our autonomic nervous system activity. So Craig's model in particular, which is the emotional moments in time model, suggests that when we experience lots of emotional moments in time, and these are typically conceptualized as being lots of increases in sympathetic nervous system activity, time flies by. And when we experience a lack of emotional moments in time, or an increase in parasympathetic nervous system activity, time passes more slowly. These suggestions are largely supported by lab research, which shows that an increase in sympathetic nervous system activity is associated with a longer perception of duration, and an increase in parasympathetic nervous system activity is associated with a decrease in perceived duration. However, this has never been studied in the real world before due to the obvious complexities. However, we decided to take on this task. So we aim to try and understand the role of sympathetic and parasympathetic nervous system activity in people's experiences of time in the real world. To do this, we recruited 67 participants and we asked them to go about a normal day's activity for a 6-hour period of study. Whilst they were doing their normal day's activity, they were wearing mobile ambulatory ECG and skin conductance recorders, and also a recorder that monitored their level of movement. We used these recordings throughout the day to get indexes of their sympathetic and their parasympathetic nervous system activity. So we use the ECG to create measures of heart rate as an indicator of sympathetic activity, and RMSSD as an indicator of parasympathetic activity. And for skin conductance, we calculated tonic and phasic levels of skin conductance, both as indicators of sympathetic activity. Participants were sent to do about a normal day's activity, and every hour we sent them text messages just asking them to rate how quickly time was passing in comparison with normal during the last hour, their mood during the last hour, and their level of engagement during the last hour. And what we were interested in is whether we could predict or understand the association between changes in their experience of time in relation to changes in their level of autonomic activity and their mood and their level of engagement. Obviously, the processing of this data, the physiological data, was extraordinarily complicated, and anyone who wants more information about it just needs to contact me and I can send them the details, but it's far too much for me to describe in this 3-minute talk. But what the summary of how we process the data is that we calculated, we were very aggressive in the way in which we cleaned the data. So we only accepted epochs of data in which there were no missing heart rate peaks. We then calculated the RMSSD, the heart rate, the tonic and the phasic skin conductance on the basis of what was essentially pure data, so data in which there's no missing data. We calculated them first as averages across the whole hour. We then corrected them for movement so that we could take out the role of just pure movement in physiological activity. And we then normalized them for each participant, and we also normalized our participants' temporal passage of time judgments and their emotion and their engagement data. So what we had eventually was standardized data sets for each participant. We then analysed this using multi-level modelling to try and understand the contribution of each of these factors in people's experience of time. So as you can see from the table in the results area of the poster, we were able to create a significant model of people's temporal experience using physiology and subjective ratings of engagement and mood. And critically, what we found was that heart rate and skin conductance frequency, so the frequency of skin conductance peaks, so you might consider these to be like skin conductance reactions, these were predictive of experiences of time. So the more sympathetic arousal someone experienced during the day, the faster they perceive time to be passing. And obviously our findings are therefore supportive of Craig's model in that we demonstrate in a real world complicated environment that your level of sympathetic nervous system activity is related to how you experience time. It's also predictive of how you experience time. Interestingly, parasympathetic activity is not related to our experience of time. So obviously we need much more research on this topic to try and understand why it is that time changes during normal daily life and what the underlying mechanisms are. But here we have demonstrated for the first time in a real world complicated environment the role of sympathetic nervous system activity in temporal experience. Please get in touch if you've got any questions. I look forward to hearing from you.